So in today's lesson, we're going to discuss ionic compounds. And so from grade 9, you should be familiar with what an ionic compound is. We're going to begin there and extend upon what you already know. So we already know that cations are positively charged and anions are negatively charged. We also know that negative charges and positive charges attract one another, right? Opposites attract. And so when we have these oppositely charged ions coming together, and they will be attracted to each other, that forms what we call an ionic bond. And that bond is super, super, super strong. So that happens because of the transfer of electrons. So we have, in the case of an ionic compound, we're always going to have a metal that has an extra electron that it wants to give away. And we're also going to have, I'm just going to let this start again, a nonmetal that needs an extra electron. So the metal is going to transfer an electron to the nonmetal, and that's going to create a cation and an anion that are going to be attracted to each other. Okay, so any substance that is composed of cations and anions that are attracted to each other, we call an ionic compound. So most ionic compounds are going to involve metals and nonmetals, and you might be wondering why. And so I want you to think about why that is. And so I've got here, a modified periodic table. Now what I've done is I've taken out all the transition metals because they're not really going to be involved in this conversation. So if you have a regular periodic table in front of you, you'll see that over here I have the metals, and over here, nitrogen, oxygen, fluorine, etc. And these are the nonmetals. Okay, so I want you to think about why it makes sense that most ionic compounds are going to involve bonds between metals and nonmetals. So what I'm hoping you're thinking about is the fact that the metals all have extra electrons they want to get rid of, and the nonmetals all sort of have close to full valence shells that they want to fill. So the metals are going to have extra electrons to donate to the nonmetals. Okay, so metals want to lose the electrons and the nonmetals want to gain electrons. So that kind of is a good fit. And so what I want to talk about next is how we can predict the chemical formula for an ionic compound. And I'm going to show you two different ways to do it. I'm going to start with sort of the long answer, which explains why the relationship is what it is, and then I'm going to talk about a quick way to go about getting the chemical formula. And so I've just moved to my trusty Jamboard where I can write a bunch of things down. And so again, what you should have in front of you is a periodic table. And that periodic table will allow you to remember that we can identify based on the position of elements what their most common what their number of valence electrons is. And so at this point, I'm hoping that you recognize that we can count over our rows and know exactly how many valence electrons are each we should expect based on the family that an element is in. So for instance, all elements in this first group, the alkali metals, have 1 valence electron. And we have 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, 8. And of course, we're going to skip those transition metals because they're a little bit wonky. So I notice that, I'm just going to grab my pen here, I notice that lithium is right here. There's lithium. And so lithium is going to have 1 valence electron. So I'm just going to write it out. And it has its 1 little valence electron. And then oxygen, well, oxygen is over here with, if I count over, 1, 2, 3, 4, 5, 6 valence electrons. So oxygen has 6 valence electrons. So I'm going to just draw those in. Here we go. There's my 6 valence electrons on oxygen. So at this point in time, neither of these elements are happy. Neither of them are stable. We've got lithium here with its, 1 valence electron. We've got oxygen, which has 6 valence electron, wanting to get 2 more. And so our metal in this case is going to want to donate. So let's just show how that might work. So lithium is going to want to get rid of this electron. It's going to give it over to oxygen, right? And so then, lithium is happy now, but oxygen is not quite happy because it's still missing 1 electron right there. And so how are we going to deal with this? Well, all that means is that we need to have another lithium atom available to donate its electron. And so here we go. So lithium, the second lithium is going to be available to give oxygen the other electron that it needs. And so now each lithium atom has supplied electrons to the 1 oxygen atom. And so what that means in terms of chemical formula is that in order to balance the charge, I needed to have 2 lithium atoms to make 1 oxygen atom happy or stable. So my chemical formula would be lithium Li2O, lithium oxide. So what I want is for you to try the next example. And here it is. I'm just going to move my Jamboard open. And I want you to give that a try and see if you can come up with a molecular formula for the ionic compound between magnesium and sulfur. All right, so let's see if we can figure this out. So magnesium, I found magnesium on my periodic table. It's right here. And so it's in my second group. And so I know that means that it's going to have 2 valence electrons. And then I'm going to find sulfur. Well, sulfur is right here. And sulfur, based on its group, has 6 valence electrons. And so I'm going to draw those electrons out. 1, 2, 3, 4, 5, 6. Okay, and it's in the same group as oxygen, which, that tells us they're going to have the same number of valence electrons. So neither of these atoms is stable right now because neither of them has a full outer shell or full valence shell. So sulfur needs 2 electrons, and magnesium has 2 electrons to give sulfur. So that's actually just like a perfect fit, right? And so that tells me that the formula between these 2 elements is going to be MgS because I needed 1 magnesium for every 1 sulfur atom. Okay, 1 more to try. No, maybe 2. Okay. So let's look at aluminum and chlorine. I want you to give that a try, and when you're pause the video and when you're ready, we will take up the question. Okay, so I'm looking at aluminum, and aluminum is right here, and that puts it in the 1, 2, 3, third row, which means that it has 3 valence electrons. And I'm going to draw those in. 1, 2, 3. And then I have chlorine, and chlorine is over here. Okay, and so that means it has 1, 2, I count over all the way, and it's in this particular group, which means that it has 7 valence electrons. So I'm going to draw in chlorine's 7 valence electrons. And after a while, you start to know how many valence electrons an element will have just off the top of your head, because there's some that just kind of come up more often. So I'm going to draw those in, the 7 valence electrons that chlorine has. And so neither of these are super stable because neither of them has a full valence shell. Chlorine, however, is pretty darn close. And so it's going to be able to accept 1 electron from aluminum. And then that electron will fill its shell and it will be stable. Right? So now this chlorine is good. But my aluminum, unfortunately, is not stable yet. It's still got these extra 2 electrons that it needs to get rid of. So how am I going to deal with that? Well, that means I'm going to have another chlorine in the mix, right? With its 7 valence electrons. So there we go. So aluminum is going to be able to unload another one of its electrons to this second chlorine atom, right? And so that chlorine is happy as well. Aluminum's not. So what do I need? How am I going to fix this? Well, I'm hoping you recognize that I'm going to need another chlorine atom here in order to satisfy aluminum. And there we have it. So that last electron is removed from aluminum. So to balance all of my electrons, what did I need to do? Well, I needed to have 1 aluminum for every 1, 2, 3 chlorines, making my formula AlCl3. Okay, hopefully you did okay with that. Let's look at our final example. And again, I want you to try this out and see if you can do it on your own. So pause the video, give it a shot, and then come back when you're ready. Okay, so I'm going to start this by first locating my elements and figuring out how many valence electrons they have. So first of all, and so I'm going to find calcium. Calcium is right here. It's in the second row, which means it has 2 valence electrons. Okay. I have phosphorus, which is over here. And so counting over my rows, 1, 2, 3, 4, 5, phosphorus has 5 valence electrons. 1, 2, 3, 4, 5 valence electrons. There they are. So how am I going to make this work? All right, so hopefully you gave this a whirl, and if you got there, great. If you didn't get there, maybe just going through this will help to consolidate your understanding. So neither of these are stable, and both need to get that full valence shell. So calcium, being the metal, is going to donate its electron. It can donate 1 and 2 electrons to this phosphorus because the phosphorus has at least 2 holes to fill, right? 2 electron holes. So calcium is happy at this point, but my phosphorus only has 1, 2, 3, 4, 5, 6, 7 electrons. So it needs another one. The only way to make that work is if I introduce another calcium ion, okay, with 2 valence electrons. And so when I do that, this second calcium atom can go ahead and donate an electron to this particular phosphorus, making it happy. But now I've got a situation where my calcium is not happy, right? So that's no good. So what I need to do is I need to introduce another phosphorus. So I'm going to do that. Okay, remember phosphorus initially had 5 valence electrons. All right, there we go. And so the second calcium can give that phosphorus 1 of the electrons it needs. And now this second calcium is good. It's gotten rid of its excess electrons. But the phosphorus is not happy because it still has 2 electron holes to fill. So what am I going to do? I'm going to introduce another calcium atom with 2 valence electrons. And that calcium is going to donate 1 and 2 electrons. And at this point, now my calcium has gotten rid of its excess electrons, and my phosphorus now has 1, 2, 3, 4, 5, 6, 7, 8 electrons, 3 of which were obtained, from the calcium. So let's look at this overall. What did I need? I had 3 calciums that I needed, so Ca3, for every 2 phosphoruses, so P2. So there's the ionic formula for calcium and phosphorus, and that's kind of showing the long version. This is why the formula is what it is, okay? That's why it is what it is. What I'm about to show you next is going to demonstrate the quick and dirty way to get the ionic formula. So I would say 9 times out of 10, unless you're asked to explain why an ionic formula is what it is, you're going to do what I talk about next, okay? Which is called the crossover rule, okay? So at this point in the game, what I need to do is I need to remind you about ionic charges and the trends on the periodic table with ionic charges. And this is why I emphasize how important it is for you to understand those pieces beforehand, and that every step moving forward is going to rely on you having a solid foundation with the ideas previous. So just to remind you, and I'm going to put them up here, you know, and they're actually written in your periodic table, but it's helpful to just kind of have an idea just visually without having to look at each one. You know, every metal ion in this first group is going to form an ion with a +1 charge. Every ion in this second group is going to form an ion with a +2 charge. Okay, so that means like beryllium, magnesium, calcium, and so on. Now I'm going to skip over, and every element in this third group here, remember we're not going to deal with our transition metals this year, though you can see if you look on there, there are charges indicated, but there's no trend that we would understand at this point. Okay, so, you know, all elements in this group right here, starting with boron, would have a +3 charge as an ion, and this is like the most common ionic charge. Okay, we're not really going to worry about carbon too much. Okay, let's not worry about that too much. You know, it can either gain or lose 4 electrons. We're not going to worry about it. Okay, remember our noble gases really don't form ions, so we don't really need to worry about them in ionic compounds. Fluorine, so all fluorine and all the other halogens are all going to form ions with a -1 charge. Oxygen, -2, oxygen and everything below. And then our nitrogen and everything below nitrogen are going to form, I'm just going to write this up here, -3, okay? So again, +1, +2, +3, and then we go back from the noble gases, -1, -2, -3. And that's that. Okay, so we're going to need to know those ionic charges, at least how to find them on a periodic table, to use this quick and dirty method to get the formula for ionic compounds. Okay, so let's do the same or similar examples to what we saw last time. Okay, and so here's what I'm going to do. I'm going to say, all right, well, I have lithium. I'm going to write out its symbol, and then I'm going to find it on the periodic table. Here is lithium, which means lithium as an ion forms an ion with a +1 charge. Okay, and then I have oxygen, and oxygen is over here, and it's in the column where it's going to have a -2 charge. Okay, now how I get the chemical formula is I simply cross over the charges, okay, the value of the charge, I should say. The negative and positive won't matter at this point. And I'm going to cross that down. So, and then I'm going to do the same thing with my 2, and that will become the subscript below each of my elements. Okay, so lithium, we'll get this 2 brought down, and the oxygen will have this 1 brought down. And sort of in a similar way in math, how we would say, you know, 1x is really just x. If it's a 1, we understand, you know, that if we don't write anything, it's understood to be 1. So typically in science, we would say, well, we would just write this as Li2O, and that's our formula. Okay, I would like for you to try this on your own in the next example. Okay, so in this case I have aluminum and oxygen, and I would like for you to find out the formula, the ionic formula, for the compound formed between aluminum and oxygen. Take a minute to go ahead and do that. Okay, I'm going to take this up and we'll see how you did. So first of all, we have to find aluminum. Aluminum is right over here, and I'm hoping you could see on your periodic table that aluminum has a charge of +3. And then we go ahead and we find oxygen, and oxygen has a charge of -2. So then all we do is, I like to do this little setup here where I just write the elements down. And then I go ahead and I take the charges. This charge here is going to go down beside oxygen. Right? So there's a 2 there, 3 there. Okay, and then the charge on my oxygen, this 2, and again, remember, the positive or negative doesn't really matter when we're using the crossover rule and creating subscripts. That 2 is going to go beside my aluminum as a subscript, and I'm done. That's the formula for aluminum oxide, the formula formed between aluminum and oxygen. Okay, let's try one more, calcium and sulfur. So you guys go ahead and try this, and then we will come back together in a second and take it up. Okay, so calcium. Let's find calcium. I'm just going to write it out here. And calcium is located right here, and its charge is going to be +2. And you can see that in the upper right-hand corner, right? Sulfur. Sulfur has a charge of -2. Right? And so when I cross these charges down, let me just do my setup here, Ca and then S. When I cross these charges down, the 2 is going to go here, and this 2 is going to go down there. So I end up with a 2 and a 2. Now the thing about ionic compounds is that these numbers that are here, this 2 and this 2, are really just representing a ratio, right? In other words, when I go back up to the top here and I say, well, I have +2 and -2, those charges will add up to give me a neutral molecule, right? +2 and -2 add up to give me 0, which is neutral overall. And so really, all I need to know is that if I need 2 calciums for every 2 sulfurs, that's really just the same as saying I need 1 calcium for every 1 sulfur. And so in ionic compounds, what we would typically want to do is reduce that ratio of 2 to 2 to lowest terms. And so that becomes a 1-to-1 ratio, which would be Ca1S1, which in turn we would kind of eliminate those ones and just write CAS. Okay? Going back to I've been in Jamboard to do these examples. I'm going to go back to my Google slide presentation, and you can write a little bit down about that. Okay, so this is the little blurb I have about that. Okay, remember that because they're a ratio. Okay, the formula for ionic compounds is they're always reduced to lowest terms. Okay, and that's it. So we've got one more topic to talk about, and that is the physical properties of ionic compounds. I'm starting you off with this one, but you'll have an investigation to do comparing ionic compounds to molecular compounds in a little bit. But this one physical property didn't really fit that well into it, and I wanted to address it myself. So physical properties basically are properties about that particular substance that help to identify it. Okay, so one property that we say about ionic compounds is that they are brittle, okay? You know, ionic compounds are often crystals, okay? And they form those crystals, but those crystals are brittle. So, oopsies, I'm just going to go ahead. So what I see here is I can see that I've got a crystal structure of anions that are negative and cations that are positive next to each other. So anion, cation in a repeating pattern which forms the crystal. And so what we see when we hit a crystal like this with a sharp object or a blunt object and they shift, right? We see this shift happening when we hit a crystal. What happens is it shears it in a nice kind of smooth way. And the reason it's able to do this is because when we shift those ions, we can often align cation to cation and anion to anion. And what we learned from grade 9 electricity is that like charges will repel each other, right? So that will create a nice smooth shearing effect on our ionic crystal, causing them to sort of break evenly. Okay, so they're brittle and will break apart sort of sharply because of those aligned ions of like charges. Okay, so as I mentioned, you're going to be learning more about the other physical properties of ionic compounds during an inquiry assignment that you're going to see at the end of today's lesson in the unit plan. As always, reach out and ask for some help if you need it. I'm happy to help you as much as you want, so just let me know.